Welcome back to another lecture on differential equations, more specifically the ordinary differential equations. This is my last lecture video for ODEs before I start moving on into PDEs, which I'll be taking full on control, and my buddy Axel will just carry on with the ODE section. So in this lecture, we're going to be discussing on how to solve linear systems of differential equations. We did an example on solving a linear system, however, it was more for a 2 by 2 system and it kind of just involved converting it into a second order ODE with constant coefficients, but we know for a fact that this may not always be the case. So this is going to be more of a general way to solving linear systems of differential equations. So before we get started, I want to do a quick little review on first order systems. And as I mentioned in the last lecture, it is possible to take a higher order differential equation and convert it into a first order system. An example on how a first order system looks is just x prime of 1 is equal to a11 x to the 1 all the way to the very end, and it goes all the way down to x prime sub n. And so we can create a solution consisting of n linearly independent solution vectors, x1, x2, and x to the n. And our general solution of the system will be x to the t is equal to c1 x1 plus c2 x2 all the way to cn xn. And so now this is where the new part comes in, solving first order systems. So to solve the linearly independent solutions, we can use the characteristic method where we let x to the n is equal to the rt. The only difference is we're going to substitute r to be lambda, and we are going to put it in matrix form. As you recall last lecture, I did mention that you can put a system into a matrix format. And so our solution will be x to the t is going to be equal to the column vector of x1, x2, all the way to x to the n, which is going to be equal to v1 e to the lambda t, and then v2 e to the lambda t, all the way to vn e to the lambda t. Because they all have e to the lambda t, we can factor out the lambda t, and then we can make v1, v2, v all the way to vn become a column vector. And so our general solution will be the column vector v times e to the lambda t, where lambda, v1, v2, and vn are all appropriate scalar constants. Now we can find the constant v to make this a valid solution. And so if we let x to the I equal to vi e to the lambda t, which is the individual solutions, then its derivative will just be using the chain rule. Not the chain rule. Is it the chain rule? Yes. No? Well, it's the derivative of a exponential, which will be lambda vi e to the lambda t for I is equal to 1, 2, all the way to n. In other words, a positive integer. And we can now start substituting in our linear system, or in other words, change our linear system to x prime equal to ax, where all these are all matrices or column vectors, and a contains the constants from the previous slide, like I mentioned, the a11, a12, and then like all the way to an. And so when we substitute the x prime and x, we get lambda v times, well, v is the column vector, e to the lambda t is equal to matrix A times the column vector v times e to the lambda t. We can cancel out the e to the lambda t on both sides, thus getting lambda times v is equal to av. Now, this looks very familiar. Where have we seen this before? Well, we've seen this in linear algebra. This is the eigenvalue and eigenvector problem. And so we know for a fact that there exists a lambda such that when it's multiplied by the column vector, it is equal to the matrix, the original matrix, multiplied by the same column vector. And to solve that, well, we just get lambda multiplied by the identity matrix, subtracted by the original matrix A, then multiply that all by the column vector V, and that must be equal to 0. And so this becomes a homogeneous system that has non-zero solutions if and only if the determinant of lambda I minus A is equal to 0. And this is known as the characteristic equation, with a polynomial with degree n on lambda. And so the solutions will give us the eigenvalues. Wow, we've heard this before. So now what do these eigenvalues tell us? So in the linear algebra, page, we discussed and we talked about different eigenvalues where we have real, complex, and then repetitive. And so the first one we're going to talk about is the distinct real eigenvalues. And this will just give us, this was just kind of like regular numbers, or just regular numbers, nothing out of the usual. And this will give us a solution to be C1 V1 e to the lambda 1 of t. And then the second solution will be the same thing, but it's just kind of different v and then different lambda. And so this is where vi is the eigenvector for the corresponding lambda I. So once when you find the eigenvalues, we have to find the corresponding eigenvectors, and those will be your solution. Now, obviously, the general solution will be the sum of all of these individual solutions. So it will be the sum of x1, x2, all the way to x to the n. The second case that we have is the complex eigenvalues. We discussed, and we're going to continue discussing, about the situation where our lambda gives us a complex conjugate. So it's going to be in the form of a plus or minus bi. And so what we do is we take the real parts of both the eigenvalue and eigenvector, which will be equal to p plus qi, and then have the general solution, or I guess the individual solutions, to be the first one being e to the pt multiplied by a cosine of qt minus b sine of qt, and then the second solution will be e to the pt times b cosine of qt plus a sine to the qt. And so if you want to find the general solution, then you add both of those two up. And the reason why we have sines and cosines is because we're using Euler's formula. And I will do a separate short video on just pretty much deriving the solution and like why this makes sense. So keep a lookout on that one. Now the third and quote unquote final case will be the eigenvalues with a multiplicity of 1. Now we discussed about multiplicity in linear algebra, and we also talked about geometric and algebraic multiplicity, and the fact that the algebraic multiplicity is always greater than or equal to the geometric multiplicity. So this kind of has two subcases, and the first one will be if the algebraic multiplicity is the same as the geometric. So if they're both the same, then we just carry on like the case for the real distinct eigenvalues. It's nothing out of the ordinary. So that's the good part. The not so good part is when we have the defective eigenvalue case, and that's when the geometric is not equal to the algebraic multiplicity, and these are not so nice because we have to deal with the Jordan canonical form. And so what we have to do is we have to find the Jordan canonical form. And again, this is all discussed in the linear algebra page. So if you want to look at that, there's going to be a tab showing up like somewhere around here. So once when we found the Jordan canonical form, we are going to have our general solution to be very similar to the case of having more than one solution or more than one root be the same in solving a homogeneous ODE with constant coefficients. So when we talked about solving homogeneous ODEs with the constant coefficients, and we had roots be repetitive, then we kind of had our solution to be like C1 e to the RT plus C2 t times e to the RT all the way to Cn t raised to the n times e to the RT. So it's going to be very similar, but instead of multiplying it by t to the RT raised to the n, we are going to be multiplying it by t raised to the n over n factorial. So the first case will be t to the 0 over 0 factorial, which would just be v1 e to the lambda t. The next one will be t v2 e to the lambda t, and then the other one is going to be t squared over 2 factorial v3 to the e lambda t all the way to t to the n over n factorial v and e to the lambda t. And so that'll be it for this lecture. This was kind of a long one. There are going to be examples for each of these 3 or I guess 4 cases, and that will conclude, except for the DE short for the complex value. But that will conclude my portion of ODEs, and I'll be seeing you guys in the cheat sheet, which is something that you guys should be interested in, and the PDE section of this page. So thank you guys for watching, and I'll see you guys in the Blackboard.